wave, the bouncing ball, the source of the wave, this guy's doing this, so it has a particular wavelength and frequency, it's not doing random movements, right? And generates this wave on the water. So guys, the nice thing about water is that it's a very visual thing. So I can be out there, right? And then I would have to have a description of this wave, right? I don't know if you can see. You're squinting. You can't see anything? You can see? Okay, that's the important part. Maybe, yeah, hopefully what I'm saying makes sense too, but we'll see. So if I'm far away from the source, you can already see that the waves look very, very nice and uniform in the sense that if I move a bit further away or to the left or to the right, the amplitude of that bobbing, right, that I would be feeling, which I was I couldn't get a swimmer. I just found this crazy person, but dancing, that's fine, would be bobbing with an amplitude A0, so it's no longer dependent. I'm far away enough that the amplitude is constant, A0, all right? But it will be oscillating back and forth, right, by a certain frequency. And if I move a little bit around that point, actually the amplitude will be exactly the same. It's just that when that amplitude is maximum, depends, because as soon as I change my R, then of course we have the term omega t, and that omega t will tell me when I'm at the maximum amplitude or at the lowest amplitude, or in fact zero, right? There are situations where certain times that I should have sign of that argument be equal to zero. So if I'm over here, all right, I will be bobbing. So if these two communicate, they will be saying bobbing with a certain frequency. The same for both. You can see that the amplitude for the one on the left is a little bit different from the one to the right, right? Maybe the one for the right is at a maximum, at the crest of the wave. The other one is at the bottom. But as far as communicating and describing their motion, right, it's the same. It's just occurring at different times. But overall, it's sort of the same thing, right? I'm going up and down a certain frequency, and that's that. But the story completely changes when I add a second source, also creating these circular type of waves. When these two come together, okay, they form what we see here is a pattern. So now how do I describe the wave, that the amplitude, right, for this dancing girl? Well, now I have to worry about the fact that there are two waves being generated, one by source 1 and one by source 2. They have the same form because, of course, if I remove one, it looks exactly the same as the other one, except that now, relative to that second source, the distance to the source will be different, right? That's only, like if I remain on the original, from the original picture, let's call it that R1. If I remove that bob and I keep the other one and it oscillates, the only thing that changes is now the distance relative to that source, right? So each one independently by superposition, right? What superposition? Add one as the other one that wasn't there to another one as if the other one wasn't there. So ignore the other one, just put that there, sum it with the other one, and you get superposition, right? And we found that I could rewrite this whole thing into a function that has an amplitude that now I call B, that depends on the difference in path length. Okay, so this is the distance from the source 1 to me, if I'm the dancing person. R2 is the distance between source 2 and me. So the difference, and I call that difference in distance the difference in path length, all right, corresponds to my amplitude. Note that it doesn't depend on time. It just depends on where I am, okay? And then it's multiplied by a term that looks like these other ones. It's a K times L, but now L is the average distance between the two R's, so R1 plus R2 divided by 2, and the angular term that bobs up and down. So you can think of this now as a new amplitude, right? Which depends on that difference in path length. Right? Path length, the difference in going from source 1 to me to minus the distance between source 2 and me. Okay, that's the path integral. All right, so that's what I have. If I'm a circumdancer, all right, I think I do have that. Well, let's say now if I look, I moved. So by moving to a different spot, I'm basically moving that difference in path length, right? Maybe not even, I mean, just moving things a little bit, but then this will be very different. As you can see from the picture, I moved from a place where I had waves to somewhere that I actually had no waves, right? That it's exactly sitting where there's no ups and downs. It's just very calm, right? So, and that is independent of time. That's the amplitude, no matter what the clock is saying. So for her, the amplitude is 0, all right, if she's there. The quality of the point is that the difference in path length, all right, as we, it has a certain characteristic, all right. One possibility is, well, let me go back a little bit. But if there is a minimum, that means that this amplitude is 0. How is this amplitude 0? By the fact that this is somehow a multiple of pi, right? If it's a multiple of pi, the cosine of that multiple of pi gives me 0, so that's how that amplitude becomes 0. All right? If I am not in a condition where this is a multiple of pi, then say I'm somewhere like in the previous slide, I moved her a little bit to the left, right? Over there, then this is not 0. This is a small number, right? But the amplitude is a smaller number than A0, right? It just moves slightly, and you can see she's at the very edge. And so it's going to be oscillating, but it cannot be like super large. It's just barely moving up and down. That means that the cosine is actually somewhat of a small number, right? It's giving us a very small fraction of the total amount of A that it could actually have. And I think I forgot a factor of 2 then. I will have to add the factor of 2 in my slides. So now, okay, so that's when it's 0. If I have another person standing in a different point, you can see for that person the amplitude is actually, and I have a typo, it's 2A. Twice, because two waves adding, there are points where they truly add, so it's 2A. All right? So this has a 2, all right, in here. So that B is 2A, twice the amplitude, right? So over time, she's saying, oh no, I'm in a wave that bounces from with an amplitude of 2A and is bobbing me up and down, and she's saying, what are you talking about? There's nothing going on here. Completely different stories from before. Before, the things were basically the same for both, no, and occurring at perhaps a little bit different times, but the description of what was happening to them was the same function. Now, they're telling the world they're telling each other a totally different story. And that's because the amplitude now depends on where you are. Before it wasn't dependent on where I was. The maximum amplitude was A, and that was that. Now it does depend on where I'm sitting. It can go from 0 to 2A. All right? So we found that the argument of that function, all right? Again, B, I have a typo there. B is equal to 2 times A0 cosine of K R1 minus R2 over 2. Okay, that's it. Right? All right. What was I gonna say? All right. So we noticed that in particular we noticed that B is equal to 0, right? When the argument K, which now I'm gonna call delta R. Okay, so this is the difference in path length, delta R. All right, is equal over 2 is equal to a multiple of pi, right? And that, right? Is that, no, that's, sorry, that's not a multiple of pi. B is equal to 2A, right? 0. It's maximum when this cosine is plus or minus 1. Plus or minus 1 is when the cosine, this argument, which is k r delta r over 2, is a multiple of pi. Now, interestingly, when b is equal to 0, k delta r over 2 becomes an odd number of pi over 2, right? Pi over 2, 3 pi over 2, 5 pi over 2, etc., etc. This gives you a 0, all right? Now you can work yourself backwards in terms of lambda, right? Because you can say, OK is equal to 2 pi over lambda. K is equal to 2 pi over lambda. So what we got from these two expressions, all right, was that the pi goes away, right? Here the 2 goes away. Here the pi goes away. And I get that the path difference is equal to m lambda, and we call this constructive interference. Constructive meaning we have the 2a condition, and it's equal to 2m plus 1, all right? Where is this? These two cancel out, right? Over 2 lambda, and that's destructive. And destructive means it just, indeed, the amplitudes just cancel each other out, all right? That's the most general thing. And then we're going to study two cases. This is just general. We're going to study two cases. One was a two-slit experiment by Young. This was an important electromagnetic waves were waves. So they had to, and when they see light, they see just like a straight. How are you going to get to prove that they are waves? They have to, if they're waves, they should behave like water waves, right? They should have an interference pattern. So Young designed an experiment that would be having two slits, and light would go through, and it would be equivalent to these two bobbing balloons, all right? And if I put a screen, I should see a pattern similar as if I had you see, imagine, I know this is circular, but imagine a flat pattern. This one will be showing a maximum, this will be a 0, this will be a maximum, this will be a 0, so that's the pattern. Maximums, maximums, minimums. So that's what he designed. In that case, all right, I'm sorry, here's basically what I wrote here. No, that we have constructive interferences. The delta R is proportional, or not proportional, because m has to be an integer, right, of lambda, and m is a counting, right? It's a number, it's an integer. So m is equal to 0, plus minus 1, plus minus 2, plus minus 3, etc. Okay? So the first maximum is when m is equal to 0. When m equals to 0 means delta R is equal to 0. That means R1 is equal to R2, right? The first dark region or calm region in the water waves is when m is equal to 0. So that would be lambda over 2, right? So when the difference in path length is half a wavelength, we have a dark or calm region. When m equals to 1, we have the next bright spot. It's a difference in path length of lambda, and so on. So the bright and dark oscillate between each other, right? All right, let me see what I have here.
So if there is ever an odd number that is divided by 2, then it's going to be a destructive interference.
Yes. The path, not just that, the path difference, right? When the path difference is an odd number times lambda over 2, it's destructive interference. You have destructive interference. All right, so because now we have light, oh yes? B is the amplitude that now corresponds to, oh, okay, well, let's see, we have to go back here, okay? By the way, I have a typo, this is a 2, there's a 2 there. Basically, when you have two waves, you can think of it as an amplitude that depends on the difference in path length times as an oscillating function, like you're normally used to, where this amplitude now can be A0 or 0, or anywhere in between, right? And the 0, whether it's 0 or 2A, will depend, 2A would be the maximum possible amplitude, so we call that constructive interference. And so this argument of this PR, K delta R over 2, K delta R over 2, K is 2 pi over lambda, is a multiple of pi. If it's a multiple of pi, cosine of a multiple of pi is plus or minus 1. But if that K delta R over 2 is a multiple, an odd multiple of pi over 2, then the cosine is always 0. Pi, 3 pi, 5 pi, 7 pi. Okay? So this amplitude can be 2A all the way down to 0. And kill that, and it doesn't depend on time. It will forever be like that. So when my cartoon was that these two kids were describing what was happening to them, and one was going, "Wah!" And the other one was like, "What's up with you? I mean, everything is very calm here. What's going on? We're on the same time." No? And that is a 2A, sorry, it's a type. Alright, so now this is light, so we cannot see that oscillation going back and forth, right? That's part of the problem. So we talk about intensity, right? That's the intensity of the light. What is the intensity of the light of the two waves that are coming together at one point in space called C? Well, it is, I have to add, right, the two waves, C1 and E2. I take I square it, I take the average, remember? All right. And I have this, you have to remember that I, right, I is equal to the average of the pointing vector, all right, and the pointing vector is E cross B over mu 0, and so we have to take the average of that, right? And then B is equal to E over C, so that becomes, and these two are perpendicular to each other always, right? So that's E squared over C mu 0, average, but E, all right, E, E, it's an amplitude, and then we have, for example, sine minus omega t, right? All right, so I have to take the average of this squared function, so this, the average of E squared is equal to the average of E0 sine, so E0 squared sine squared of Ki minus omega t, which is equal to E0 squared times the average of sine squared Ki minus omega t. And what is that average? Do you remember? It's equal to 1/2. All right? So this is equal to E0 squared over 2C mu 0. All right? So, that's when I have the same wave, right? But now if I have two waves, right? Now if I have two waves, then it's this. S1 plus S2. So, this is what's represented here, right? Now, what happens is, because we already know what is, in this case, E would be given by this, E0, and then sine of KL minus omega t, right? The square of this, again, I have a sine squared like this, and this is only depending on the space. So I get something that simply the square, all right, I0 is just the coefficient at the beginning, and the coefficient, I'm defining this argument, okay, this argument, I'm defining it as phi over 2. So the intensity is equal to some maximum intensity that is 2E0 with mu zeros and C's and halves, okay, that doesn't depend on anything, they're constants that go in this I0, cosine squared, right, because we need the intensity is the square of the electric field, right, cosine squared of phi over 2, and that's that, because I absorbed the 1/2 in the I0, all right? So the intensity is described by simply a cosine squared function where the angle is again k delta I, right? If this is phi over 2, that means that phi is equal to k delta I, right? I should just say without the parentheses, so it's not confusing, like a function of, right? All right. Again, the intensity will be maximum when, what should the argument look like? I would say the intensity would be actually, sorry, E1 plus E2. Plus a constant here. I wouldn't say C, I'm gonna put gamma. What should be, right? So we have that the intensity is maximum when this cosine is 1, right? It could be cosine of plus or minus 1, but since it's squared, it will be 1 no matter what. So what should this angle be?
90.
Sorry?
70.
The phi should be pi by 2? No, so tell me. So I equals I0 cosine squared of phi over 2, right? And phi is equal to k delta I, right? So what should phi over 2 be to get a maximum intensity? One possibility is 0. What other possibility? So this has to be equal to m pi, right? Where m is equal to 0, plus minus 1, plus minus 2, etc. Right? That would be the case of constructive interference, right? That gives you the maximum intensity. If you wanted to go to 0, the intensity goes to 0. What should be that angle?
180.
Pi, 3 pi. Sorry? You said it's so low that I cannot hear you, but let's assume that you said this. I'm assuming that you said this. Correct? And that would be discontinuous, right? So you basically get the same result as before, all right? Because this is simply k delta r over 2 as we had before. K is 2 pi over lambda. And again, the condition, whether I write it as an electric field or the sum of two waves or the intensity of two waves, I get the same thing, right? So the intensity is simply given by that, by this function. now, in the case of the two slits that Young played with, he put the screen quite far away, so he could do some mathematical approximations. The mathematical approximation is simply that he puts the screen so far away that he can approximate delta r as d sine theta. Whose theta? The angle that the line that goes from the middle of the slits, the two holes in the screen, all the way to the screen, that's the angle theta, because in this approximation that Young made, these two rays are parallel to each other, and therefore parallel to that red line, right, the midpoint line. And so d sine theta is simply that little bit of a difference between the two rays before they get to the screen, right? Difference in path length. This is a little shorter, this is a little, the one on top is a little longer, and it's a little longer by d sine theta. D is the distance between the two holes that generate the pattern, okay? And theta is the angle that these two rays basically are making with the horizontal, okay? Yes? So in that approximation, everything remains here the same, except that I replaced R1 minus R2, the difference in path length, with d sine theta. So the angle becomes k d sine theta. Now I'm going to make another approximation. The approximation is that I'm looking at the screen pattern really close to the midpoint of the screen and seeing how those bright spots and dark spots behave as I move along this screen away from the center. So the approximation is that L, the distance that I'm going to see away from the center line, down or up, it doesn't matter, relative to how far the slits are from my screen, is super small, meaning the distance from the center to where I'm trying to see whether I have a dark spot or a bright spot, relative to how far away the screen is from the two slits, is really small. In that case, all right, it means since sine over cosine is tangent, when this is very small, okay, when this is very small, it means that sine theta is very small and cosine theta is almost 1. So in this approximation, the sine over the cosine is approximately sine, which is approximately theta. So in the small angle, what we call that the small angle approximation, sine theta is approximately theta. All right? All right, so the final result here, all right, so the difference in path length when the angle is very small, it's approximately to d theta, okay, d theta. So delta r is approximately equal to d theta in this, when I'm looking very close to the midpoint and the screen is very far away. So now, I can ask you, all right, so now I can grab this form, put it in here, and what I get is that, remember when we got that, so d theta times k over 2 equals m pi for constructive, or 2m plus 1 over 2 for destructive. Alternatively, since k is 2 pi over lambda, I can write that theta, the angle at which I see different, either a maximum or a minimum, is equal to the 2 pi here, the 2 pi, the 2 cancels with this, so I have a pi, the pi cancels with these 2 pi's, and then so lambda over d times m, well, times m gives me constructive interference, and times 2 times m plus 1/2 for, so this is constructive and this is destructive, right? And m again is equal to 0, plus minus 1, plus minus 2, etc. So the angle at which you have maximums are multiples of lambda over d. The angles at which you have destructive interference are lambda over the d times this integer plus 1/2. Okay? So, there was this question of what happens when the wavelength increases. All right? So, will we always have a bright spot in the center of the screen? Yes, because at that moment, the difference in path length between the two rays is the same, right? There's no, it's 0. The path difference is 0 because the distance of both rays to the center of the screen is the same, right? If you go from S1 to the center and S to the center, the R1 and R2 are equal, so the difference is 0. So there will be, since M is equal to 0 here, that corresponds to constructive interference. That would be a bright spot. Next follows M equals to 0 for destructive interference. So 1/2 of d lambda over d is our first minimum. Okay? So let me draw this intensity as a function of the center of the. So we have a screen here. All right, we have a screen, and we have intensity. What color? Blue. All right, so this is the center of the screen. We have a maximum, and then we have this cosine function doing this, right? And so this minima, so this corresponds to first maxima, center maxima. Then this would be the first minima. And the distance here, all right, this distance corresponds to 1/2 lambda over d, right? Now the first maxima, here m is equal to 0, here m is equal to 0. This is the first maxima. Okay, it's symmetrical. This is also the first minima, and this corresponds to the first maxima, but they're symmetrical relative to the center of the screen, right? So here we have source 1, source 2, and they're separated by a distance d, and this is the midpoint of the two. So the first maxima, which is m equals to 1 plus minus 1, all right? Then we go back here, m is equal to 1, so that's lambda over d. So this distance, this angle, right? The angle made for the first maxima is theta, all right? For that theta, this is theta minimum, where m is equal to 0, is that theta for maximum of first minima, of the first one, will be lambda over d, right? And so on and so forth. So let's look at this angle, which is lambda over d. If I increase lambda, what happens to the angle? Increases. If d becomes smaller, meaning the two sources get closer together, okay, what happens to the first maximum?
It's bigger.
It's bigger. So either the wavelength becomes larger or the distance becomes closer together. The maximus here, it will start to spread out, right? In particular, I want to talk about the wavelength. If I change the wavelength, given that the separation is fixed, all right? If I make the wavelength larger, the maximum, the first maximum, well, the maximums will start to spread out. And that was the point of this picture, all right? So if I have different wavelengths, all right, the longer the wavelength, so this is the first, this that you're seeing are the first maxima. So the first maxima for the red is further out, a bigger angle than, for example, the blue. You see that? Here it's all of them together, making a white spot, because for all wavelengths, it doesn't matter. The center peak is the maximum. So all of them, all colors coincide at the center, and it's white. But as you move away from that center peak, where the next maxima will depend on the wavelength. So the first wavelength that you see with the first maxima will be blue. The first maxima for the red wavelength will be even further down, as you can see from this.
So basically, higher the wavelength, the more distance there's going to be.
Right, that's what this says, right? Yes, any questions? All right, so now let's do a problem. The figure below shows the interference pattern obtained in a double slit experiment with light of wavelength lambda. Identify the fringes that result from the interference of two waves whose path differs by exactly 3 lambda. In the path difference, okay, delta r is 3 times lambda. All right, I already erased it, but okay. Here we can do it. I can do it again. So here I could put k delta r over 2. K is 2 pi over lambda. All right. So that this goes away, and what I end up with is that delta r equals, right, lambda times m for constructive, and m 2m plus 1 over 2 lambda for destructive, right? So they're telling you that the difference in path length is 3 times lambda. Is it constructive interference or destructive interference? Constructive interference, right? So they're asking for bright fringes. Identify the fringe or fringes that result from a difference from the interference of two waves whose path differs by exactly 3 lambda. All right, so this is the central central fringe. What is the path length difference for the central fringe? 0. All right. So the next bright fringe above and below the center one would be m equals to plus or minus 1. So b lambda. All right. So the next bright fringe would correspond to 2 lambda. And finally, the third one would be 3 lambda. So what's the answer? E. Exactly, because it will, right? E. It's 1, 2, 3. The first, this is the central fringe, first, second, third. This is the first dark fringe, the second dark fringe, the fifth. The only thing that's confusing about that is that for the first dark fringe, m is equal to 0. Okay? The same double slit experiment is immersed in water, which has index of refraction 1.33, and repeat it. When in the water, what happens to the interference fringes? What happens to lambda when it goes through a new material? It becomes smaller. So what happens to the fringes? Let's look at the first fringe. If the lambda becomes smaller, then what happens to the first maximum? It gets closer to the central fringe. So it goes in, right? Exactly right. Okay? They're more closely spaced, the maximums. Okay? By that factor of n, if you remember. The new lambda is equal to the lambda in vacuum over the index of refraction. Right? All right. Again, the intensity is simply that I0, which is the maximum intensity possible, which are all these E squares, mu zeros, C's, etc., and 1/2, all into 1. All right, where that angle phi, phase difference that we call phase difference, is just K times delta R, right? K, R1 minus R2, or R2 minus R1. All right, next question. In a two-slit interference pattern, the intensity at the peak of the central maximum is I0, right? That it has to be, because at that, the phase angle is 0, right? Question mark phase. Phi is the phase angle, right? And the phase angle is related to the difference in path length. At the center of the screen, the two rays have the same distance to it. So this is 0, so this is 0, and the cosine of 0 is 1, squared is 1, I0, okay? All right, so let's say it doesn't give you a number, it just gives you a letter. At a point in the pattern, that means on the screen, all right, where the phase difference between the wave from the two slits is 60 degrees, what is the intensity? Okay, when the phase difference, now remember this phi is the phase difference. This we call the phase difference. All right? The phase difference. So when the phase difference is 60 degrees, what is the intensity? What is the intensity? Did I erase it? Again, I is equal to I0 cosine squared of phi over 2, where phi is the phase difference. If the phase difference is 60 degrees, then what is the intensity? Are you thinking? No? Yes? You're like in the middle. You're not in a maximum, you're not in a minimum, you're somewhere in between.
I naught by 4.
Sorry?
I naught by 4.
I naught by 4, right?
I was about to say 3 I naught over 4.
You were going to say what?
3 I naught over
3 I naught over 4. How did you get
4. That's 60 divided by 2 is 30.
the cosine of 30 is? No, that's right. No. It's one. But you're correct. I mean, your math was correct. It's the number you calculated in your head was not correct. But that's okay. You got the right thing. Okay. What is the path difference for light with a wavelength of 40 nanometers from the two slits at the point where the phase difference is 60 degrees? What is the path difference? If this angle is 60, should I use degrees? What should I use?
Radians. Radians.
Radians. Typical mistake of the exam. Combining radians with degrees. Obviously, we use that as a trick. We give it to you in degrees. You have to transfer it into radians, and then you can solve the problem. Okay? So, how many radians in 60 degrees? Right? That's exactly right. Now get what is the path difference. They give you the wavelength, 400 nanometers. What is K?
2 pi by 1.
2 pi over lambda. And that's how you get delta R, the path difference. Right? And that's that. Again, that phi in, I don't highlight it here, unfortunately, but in radians, okay? Good? Next problem. Two slits spaced 0.05 millimeters apart are 1 meter away from the screen, okay? So the screen is clearly super far away from the separation between the slits, okay? Coherent light passes through the two slits. Coherent light means same wavelength, same frequency, and they have now the same clock, okay? In their interference pattern on the screen, the distance from the center of the center maximum to the first minimum is 1.5 millimeters, the first minimum, okay? The intensity at the peak of the central maximum is 0.08 watts per meter squared. What is the intensity at a point on the screen that is 1 millimeter from the central maximum? So what this is saying is that the first minimum, this distance, right? This distance, we know the angle, it's this. The distance, L, right? Is 1 point, this is the first minimum. So they want to know what's the intensity when it's 1 millimeter. So this is 1 millimeter. What's the intensity there? All right. So, a quick reminder, okay? We're saying that we're looking at distances really close to the center in millimeters, and that is 1 meter away from the screen. So this angle is very small, right? This angle is very small. So, in a way, sine theta, or sine theta is this distance divided by, okay, so tan theta is approximately theta, all right? And who's tan theta? Tan theta is a distance away from the center maximum, L, divided by big L. Let's say big L is the distance between the two slits and the screen. And little l, okay, any point L, is from the center to any point away from the center. Okay, so the tangent, so this angle, the tangent is L over big L, right? All right. I sort of already gave you the answer. Because it's small angle, because it's a very small angle, here I can say that this is equal to L over that, right? So if I find L, right, I'm given L. It's 1 millimeter. I'm giving the distance of the two slits to the screen, 1 meter. Therefore, I get theta, right? All right. So, and theta is related to this by k d theta. So now I know this angle in radians. Remember your calculator. This number is in radians, so this will be in radians. So now I plug it into my I. Where did I put my I? Did I erase it? I, intensity, is I0, which they give you in the problem, cosine squared of that base angle divided by 2 squared.
So L is a slit.
L is you want to know the intensity at a distance L from the center. Big L is the distance between the two slits and the screen when you're looking at the pattern.
Oh, okay.
Okay, and L is just any distance away from the center. And usually small. You're very close to the center maximum. So that little l over big L gives you the tangent of the angle, but since it's very small, that's approximately theta. And we already had this here, so I can do this, right, to find theta. Then I can, because again I'm in the small angle approximation, in reality this is sine theta, but this is approximately equal to k d theta, which is this one. So now I can calculate that angle, the phase angle, which I then put into this formula and I can calculate the inverse.
This
Right?
K1.
Sorry?
It's K1/3.
It's what?
K.
K. 2 pi over lambda. Ah, yes.
Is it like you get it from the distance to the other maximum?
Right, exactly. Exactly right. So if the first minima is here, right? If the first minima is here, they already tell you that this is 1.5 over 1. That is the first minima, so therefore this has to be equal to lambda over 2d. They give you d, so you can get lambda. Yes? And the answer is here. All right? Try Try to go over it, try to solve it on your own. Alright? This is typical of the exam. Typical. Little changes here and there, but that's exactly what we're gonna ask.
Is this topic like a favorite in the finals?
All topics are favorite. No, well, this is one of them. For chapter 35, this is a favorite one. Definitely. Yes. No, nothing about it.
So just these new check.
Yes. No problem.
And are you? Do you have any more office hours this week?